Uh, in the last lecture, we have seen the different types of the errors, that is systematic errors, then random errors, gross errors. Now moving ahead, we are going to see what are the different sources of the errors. So where these errors come from, because in order to take the corrective action, one must know the source of the error. So first type of the error is that is called as a flexure at the contact surface. So what is this flexure at the contact surface? So sometimes you can see that flexure at contact surface is nothing but the elastic deformation at the contact point. It is the elastic deformation at the contact point, because you can see here, this is a vernier caliper which is shown, and the objective is to measure the diameter of this particular component. Now if the uh, if the correct pressure is not applied, so in that case, uh, it might happen that area of contact while setting the instrument and area of contact while taking the readings are different, and because of that we may get the wrong reading. So we have to make sure that area of contact while setting the instrument and while taking the readings both are same. Otherwise there will be flexure at the contact surfaces, and there can be elastic deformation at the surfaces, and we can have this type of the error. Then next is called as a alignment error, or sometimes it is referred as a sign error, sometimes it is referred as a cos error. Okay, so the this error is illustrated in the following figure. Now this error is based on Abbe's principle of alignment. It is known as Abbe's principle. Remember that the word Abbe's principle, which states, what is Abbe's principle? Abbe's principle states that the line of measurement of the component uh, component to be measured should coincide with the measuring scale or axis of the measuring instrument. So that this is the statement. So accordingly, suppose the objective is to measure this length, okay, this horizontal length we want to measure. So if we want to measure this length, we have to hold this scale parallel to this line, isn't it? But if we don't hold this scale parallel to this line, and if we hold the scale in this position, in say inclined line, then we are going to get the error. This called as a cos error, this is called as a cosine error. So the actual dimension is L cos theta, but you are getting the dimension as L. Okay, so why? Because the axis of the as per the Abbe's, the line of measurement is not, this is the line of measurement which is shown by this line or the scale. The line of the measurement is not coinciding with the measuring scale, okay, or the axis of the measuring scale. So this is called as a cosine errors. If it is holding perpendicular to this position, then it will be held as a sine error. So cosine error, cosine error, or error based on the Abbe's principle, so all are same, they are called as alignment error. So workpiece is not held perpendicular to the face of the anvils. This is the scale. In case of the vernier caliper, also that can happen. So this can be another source of the error. Then third error is called as a parallax error. So we have seen this, we all of us have come across this type of the error. This is a parallax error. So what is this parallax error? So parallax error occurs when the readings are taken by aligning two lines on the measuring instrument. Okay, so as you can see the objective is to measure, your objective is to take a reading, and the actual reading is say you can see this is 3, 4, 5. In between 4 and 5 there are some again 10 scales, 10 divisions are there. So 4.1 to 4.9 and then 5. So the actual reading or the true value of the measurement is 4.8 if we are looking at this dimension from this position. Okay, so 4.8 centimeter is the actual reading or true reading, but it might happen that the observer is not at this correct position. Instead of this correct position, it might happen that the observer is looking in some other direction. He might be looking in this direction, or he might be looking in this direction. So if the observer is looking in this direction, he may read the measurement as a 4.9 centimeter. So you can see here it is a 4.9 centimeter in this direction. Reverse may happen. The observer is standing here and he is looking at the measurement in this direction. So he's interpreting the reading as a 4.7 centimeters, but the correct reading is a 4.8 centimeters. Okay, so it is basically related with the position of the observer. So the observer should be positioned in must be in proper direction, and then only this type of the error can be removed. So one method to avoid the parallax error is to use the double graticule lines. Okay, double graticule lines. So it is easy to avoid this type of the error by using the double graticule lines. So parallax error is common. Many of us have come across this type of the error. Then next error is called as a placement error, or it is also called as a contact error. So what is this? You can easily see this type of the error is observed in case of the curved surfaces. If the object is having curved surface and we want to take the dimension on the curved surface, like a ring, like piston. Okay, so in such case the placement error or contact error can happen. You can go through this sketch. You can see this is the object which is to be measured. We want to measure the thickness of this particular, say a ring. Okay, and I am having this instrument. I am having, say, micrometer is there, and I am placing the two anvils of the micrometer in this fashion. This is one anvil, this is another anvil. There is no issue with the upper anvil. Upper anvil is contacting this surface at correct position, but the problem is with the lower anvil. This anvil should contact this surface at this extreme point here. So in this case, instead of contacting at correct position, the anvil is contacting at wrong position. That's why we are getting the wrong reading. That's why the contact here is wrong. That's why this is called as a contact error. Okay, so this is only due to the poor contact. So called as a contact error. Then next error is called as a placement error, or it is also called as a elastic deformation. Okay, so as you can see, this is mainly elastic deformation is mainly occurs when a heavy object is supported as shown in the following figure. So this is one figure and this is another figure is there. So we will see both the figures. So as you can see in this figure, this is the object and this object is supported on these two supports. Okay, so now the issue is basically related with the when the object is heavy, there is a possibility that this object may undergo the deflection due to its own weight. Its own weight will cause the object to bend either in say downward direction, or in say, or it may go in this fashion also. So it may bend like this, or it may bend like this, because of the because of its own weight. Now if the issue is placement of these two supports at correct position. So if we want to avoid such type of the error, the distance between the two supports, these two supports must be correct one. So ideally this distance must be 57.7% uh, of the length of the bar. So if the length of the bar is 100 mm, the distance between the two supports should be 57.7 mm. So 57.7% of the total length of the bar, that is the ideal distance between the two supports. So if this criteria is maintained, if this criteria is satisfied, then the bar is not going to bend in both the direction. So in first condition, this is the bar, and now you can see these two supports are too close to each other. They are very close to each other. That's why the bar has bent in this position like this. Okay. Whereas in second condition, these two supports are too long. The distance between the two supports is very high. That's why the bar will bend in this fashion. Okay. So we don't want both the conditions. The ideal condition is this one. So maintain the distance between the two supports, and it will remove this support error. So you can same is written over. So long bars due to self weight may undergo the deflection. So this error can be avoided. Then some environmental errors are there. So these errors are due to conditions external to the measuring device, including the conditions in surrounding the instrument. So these may be the temperature, pressure, humidity, dust, vibrations, or external magnetic or electrostatic fields. So you can see all these parameters can introduce the error in the measuring instrument. So we have discussed this before also. We have to avoid such type of the errors by providing some kind of the shields, by providing some kind of compensating devices. Okay. Take the readings in protected environment. Okay, that's why you might have studied that. You might have heard that the calibration labs are maintained at 20 degrees centigrade. So all the readings are taken at generally at the 20 degrees centigrade to avoid the effect of the temperature. Basically temperature, all the labs are they are maintained, high amount of cleanliness is maintained, humidity is maintained, it is assured that there are no vibrations can also cause introduce the errors in your measurement. So all these things we have to keep in mind. Then next type of the error is a dirt error. So as you can see, dirt particle is nothing but sometimes the dirt particles can enter in the inspection room through the door and the windows. So it is obvious that these particles can create small dirt errors at the time of the measurement. So the only way to avoid such errors is to make the laboratories as a dust proof laboratories. This is the only solution to remove this type of the errors. So these are the some of the sources of the errors. Separate questions many times is asked based on this. Now next is the next concept is the calibration. So the what is the calibration? Calibration is the most important part of any kind of the measurement. Calibration is nothing but the checking the accuracy of the measurement of an instrument by comparing it with a similar instrument that has been certified as a standard of known accuracy. It is very important. Many times this question is asked at the time of the oral itself. Many times this question is asked at the time of the oral itself. So we can say that this is the most important part of say any kind of the instrument. Now we will try to elaborate this definition. Checking the accuracy of the measurement of instrument. Suppose you take the example of the, say this, I will show you one. Suppose this is a vernier caliper and you want to ensure the calibration of this measuring instrument. So this instrument is to be calibrated, means what we have to ensure that whatever readings given by this, whatever measurements taken by this vernier caliper, these measurements are the correct readings, and they are not giving you the false readings. So how to ensure that? So what you have to do, you have to send this particular vernier caliper or this instrument to a calibration lab. In calibration lab, they have what they will do, they will take the readings of some components available with them. They know the dimension of those dimension of those parts, and they will take compare the dimension observed using this particular vernier that is given by you for the calibration, and they will use another vernier caliper available with them which is already calibrated, which is already certified, and they will take the reading with vernier caliper which is already certified, and the readings observed under both conditions, those will be compared and they will try to find out the discrepancy. So this is the basic objective of the calibration. Now what is its purpose? Its purpose is it is used to detect any discrepancies. Discrepancies means whether there are any deviations in the performance of an instrument, and if there are discrepancies are there, they will try to bring it within the acceptable limits. There is a possibility that because of the frequent use, basically generally the mechanical components, because of the frequent use, there is a wear and tear of the various components of this of the instrument, and because of wear and tear, if the maintenance is not carried out, they will start giving the false reading. So what calibration lab does, if they find that there are discrepancies in the performance of the instrument, if possible they will try to repair that instrument and try to bring it within the acceptable limits. So many times it may happen that that instrument is repairable. If that instrumentation is repeatable, repairable, they will repair it and they will calibrate it properly. Sometimes it may happen that the instrument given by you is beyond repairing. It cannot be repaired. Some of the parts are permanently damaged and you cannot repair it. Once they get assures that this instrument is beyond repairing, they will directly discard it, or they will use it as a rough indicator. Okay, so that type of the report will be given by that particular lab. Now let us take the example of the we are going to see the two examples: calibration of the vernier caliper and calibration of the micrometer. So as far as the vernier caliper is concerned, so what kind of the parameters are generally checked for the calibration of the vernier caliper. So we want to test the performance of the this instrument. So this is say digital vernier. Okay, this is a digital vernier caliper. Now these are the two anvils. This is a main scale is there. This is a digital display. So you can go through this image of the vernier caliper, and you can see that what are the parameters that are checked or during calibration. Flatness and parallelism of the jaws. So what is this flatness and parallelism of jaws? So you can see here in this vernier, this is one jaw and this is a second jaw. So the basic principle behind taking the measurement is to hold the component between these two jaws. In case of the vernier caliper, this is the object which is held between the two jaws, and this gap between the two jaws is nothing but your measurement, and that measurement is displayed here. Okay, now it is so obviously logically it is necessary that these two jaws must work properly. They must be perfectly flat. Okay, isn't it? So that has to be ensured, isn't it? So flatness and parallelism of the jaws means these jaws must be parallel to one another. Remember that this jaw and this jaw, both jaws must be parallel to one another, because the distance is measured across the two parallel surfaces only. If these two jaws are not parallel to one another, it will give you the false reading. So these are checked. Then second is zero error. So zero error means what? The meaning of the zero error is, you can again see in this particular image, this is a say fixed jaw and this is a movable jaw. When the two jaws are closed, there is no gap at all. So there is no gap at all means when two jaws are closed, there is no gap at all, then the reading shown here must be exactly 0.0000. So this is called as a zero error. Sometimes it may happen that when these two jaws are closed, you may see some amount of reading here. So it means that if there is any reading apart from 0.000 means there is some amount of error is there, and that error is called as a zero error. So this error can be positive, this error can be negative also. Okay, so this has to be checked. Then third is the accuracy of the measurement means vernier is checked for its accuracy, whether it is giving me the correct reading or not, that is to be checked. And fourth one is a hardness test of the working faces, means whatever this working faces are, these are the working faces, these are the working faces. Okay, so these working faces must be hard enough because the pressure is applied. Now we will see how these parameters are checked one by one. So let us see how the flatness and parallelism of the jaws is checked. So here flatness and parallelism of the check is can be checked by using a straight edge. So we will see what is a straight edge in coming lectures. We are going to see what is a straight edge. Straight edge is nothing but it is an instrument whose base is perfectly straight. Okay, so that straight edge will be used as a reference, and that straight edge will be kept. That straight edge will be kept on the here. For initially it will be kept here, and it will be checked whether it is perfectly flat. If this surface is not perfectly flat, then there will be gap between this surface and the straight edge. So that gap can be seen, gap can be calculated. Similarly, after this phase you have to keep the straight edge here and again check whether there is any gap between this surface and the straight edge. If there is no gap, you may say that it is a perfectly flat. Okay, then next is a parallelism of the jaws. So how to check the parallelism of the jaws? So you checking the gap between faces of the vernier and straight edge. Again we can check that. What we can do, we can put a slip gauge. We know that these we have already seen the slip gauges. Slip gauges are used as the standards, and out of this 6 faces of the slip gauges, two faces of the slip gauges are highly polished. They are the opposite faces are perfectly parallel to one another, isn't it? So you can use that slip gauge. So hold the slip gauge between these two faces. So this is a fixed anvil, this is a movable anvil. In between these two anvils you hold the slip gauge and check whether there is any gap here or here. If there is no gap between this, between surface of the slip gauge and anvil, then it means that it is a both the jaws are parallel to one another. Okay, so this is the way to calibrate the first the flatness and parallelism of the jaws. Second, how to check the zero error. So zero error checking is very easy. What you have to do, bring the two jaws together and note the distance between 0 of the main scale and 0 of the vernier scale. So what is the this is to be done in case of the analog verniers, but in case of the digital verniers you can get that display directly. So what is this? So as I told you, these two jaws are to be brought close to one another. There should be 0 gap, and when this gap is 0, the display here also has to be 0. So if this is seen, it means there is a no error, no zero error in your instrument. So this is as far as the digital instrument is concerned. But what about the analog? In case of the analog, I will show you one more sketch of this vernier caliper. Okay, you can see. So this is the analog vernier. So here you are not going to get any kind of the display. So in this vernier caliper, this scale which is on this beam, fixed beam, that is called as the main scale. On the main scale there are say you can see some numbers are shown, say 0, 10, 20 and 120. So this is called as a main scale, and there is one more scale here which is called as a sliding scale, or which is also referred as a vernier scale. On this vernier scale also there is a 0 here. You can see here, this is the 0. So how to check the zero error here? What you have to do? You have to bring this jaw close to this. So bring these jaws together. There should not be any gap between these two jaws, and when these two jaws are brought together, in that case the 0 on the main scale here, 0 of the main scale and 0 on the vernier scale, they must coincide, they must be in one line. Okay, so this is the way to check the zero error in case of the vernier caliper. Then accuracy of the measurement, third element, how to check. So it is very easy to check. Accuracy means we have to ensure that whatever reading you are taking, that is correct or not. So how to check that? What you have to do? You have to just insert the slip gauges of the different sizes between the jaws and compare the readings of caliper with the size of the slip gauge. So what do you have to do? As you can see, this is the slip gauge. We want to check the accuracy. We want to ensure that the reading given by this vernier caliper is correct or not. So what we are going to do? You have to insert one slip gauge. Now we know that the dimension of the slip gauge is absolute. It is perfectly correct. So if the slip gauge size is say 25 mm, so it means it is exactly 25.000. So what you have to do? Insert the slip gauge between the two faces and check the reading here. So the reading shown in this display unit must be exactly equal to the reading which is there is a one number on each slip gauge. There is a number. That number represents the size of that slip gauge. So size of the slip gauge must be equal to the number displayed here. Okay, so what you can do, you can take multiple readings. This is one slip gauge, then you can take one more still 2-3 slip gauges, and for each slip gauge you check the After say 25 mm, you take the slip gauge of uh, say 10 mm, then 5 mm, and observe the readings here. So all the readings must be correct. So for 10 mm slip gauge, the reading shown in the display unit of the vernier caliper must be 10 mm, and like that you can check the accuracy. Means if the readings on the slip gauge and in the display unit of the vernier caliper, if they are matching, it means that your vernier caliper is accurate. If there is any kind of discrepancy is there, we have to you have to send it for the corrective action. Then next type of the error is next type of the parameter is to be checked is hardness testing of the work faces. We have to ensure that these faces, the faces of this anvil, so fixed anvil and movable anvil, they must be hard enough, because every time the pressure is applied on the workpiece by these by the faces of the anvil, and therefore the surfaces of the anvil must be strong enough, they must be hard enough to bear the pressure applied by the workpiece on the surfaces of anvils. They should be scratch resistance, isn't it? They should be corrosion resistant, etc, etc. So hardness test must be done. So the hardness test can be done with say any available methods. Many hardness testing methods are there. Brilliant hardness test is there, Vickers hardness test is there, Rockwell hardness test is there. So you can use any hardness method, and you can check the hardness of the working faces. So this is the way to calibrate the vernier caliper. So in the calibration report, all these things will be mentioned. Then there is a calibration of the micrometer. So what is a micrometer? You might have seen this somewhere again in your curriculum. This is called as the outside micrometer. So similar to the vernier caliper, there are two you can say anvils are there. So this is a fixed anvil, this is a movable anvil. In between the fixed anvil and movable anvil, one slip gauge is held. You can see one number here, that is a 50 mm. Means a slip gauge of 50 mm is held between the fixed anvil and this movable anvil, or this is called as a spindle. Fixed anvil and this is a spindle. So this spindle can move in and out of this barrel. This is called as a barrel. Okay, so as you rotate the screw over here, okay, this is called as a thimble. So as you rotate the thimble you can move this spindle in forward direction or in backward direction, depending upon the direction of rotation of this thimble. So as you can see, this 50 mm is nothing but 50 mm is the distance across the two parallel faces of the slip gauge. So this is a one face of the slip gauge, this is another face of the slip gauge, and the distance between these two parallel faces is nothing but exactly 50.00000 mm. That kind of accuracy is maintained. So similar to the vernier caliper, we can check all the parameters, whether there is a zero error, whether these two surfaces, whether the faces of this anvil and the face of the spindle, whether those are parallel or not. Similar to whatever test we have done for the vernier caliper, all such tests can be done here also. You can check the accuracy of this micrometer also by holding the slip gauge. The additional test or additional thing what is ensured is, in this case is case of the calibration of the micrometer, we have to check for the easy movement of the parts apart from those discussed in case of the vernier caliper, because this micrometer is, whatever is a micrometer, it works on the principle of screw and nut. Everybody knows how the screw and nut works. Okay, so there is a possibility of the backlash error. So you might find out what is a backlash error. So it works on the principle that this movement of the spindle is nothing but like a screw and nut. So as you rotate this thimble, this spindle will come out of the barrel. It will advance. If you rotate this spindle in say forward direction, if you rotate this spindle thimble in forward direction, the spindle will advance towards this fixed anvil. If you rotate this thimble in reverse direction, say towards us, okay, so if you rotate it in this direction, in towards us, towards you, then in that case this spindle will come in downward, the spindle will go again in the barrel. So this movement of so there is a relation between the rotation of the thimble and axial movement of the spindle. So that relation has to be maintained, isn't it? Like a screw cutting. So there has to be, this relation is fixed. So if say thimble rotates through one complete revolution, then the spindle will advance by some distance. It will move in axial distance through some distance. So that relation has to be constant every time. If this relation is not maintained, then there is a possibility of then that is called as a backlash error. Backlash error means what? If you rotate this thimble by one rotation, the spindle, sometimes the spindle will move say by 0.5 mm, sometimes it may move by 0.52 mm, sometimes it may move by 0.48 mm. So this is not expected. Every time you rotate this thimble by one rotation, it must say advance by 0.5 mm every time. And if this is not maintained, then you can say that backlash error is introduced. So that is dangerous. Backlash error is not expected. So how to remove the backlash error? So here there's nothing complication is there. Only what you have to do, you have to carry out the regular lubrication of these parts of the micrometer. So this lubrication will reduce the possibility of the backlash error. Then this is one just sample calibration certificate is there. You can see this is the calibration certificate. This is just a format wherein there is a name of the calibration laboratory is there, then calibration certificate is there, then everything in that calibration report, date of receipt is there, date of calibration is there, then due date is also there, date of issue, challan number, everything is there. And in details, this is a customer, that is Srimati Kashibai Noli College of Engineering. Then this is the part name of the instrument, that is external micrometer is there. Then a range of that instrument is given as 0.25 mm, list count is given 0.01 mm. Then ID number is there for each instrument. Remember that for each instrument in your industry or in your organization, different ID has to be there. There has to be unique ID number. Suppose you are having 10 number of micrometers in your shop. So each micrometer will have different ID number that has to be unique, like the Aadhaar card. The Aadhaar card is a unique ID. Similarly, every instrument must be identified with different ID number. So this is the ID number, because that must be traceable. If anybody starts inquiring, then it is easy to track any instrument with the ID number. So this is the ID number given. Then reference used, then relative humidities. These are the working environmental conditions are there. As you can see, which reference is used, IS 2967 is used. Then environmental details are there. What is the temperature at which this calibration is carried out? It is a 20 degrees Celsius plus minus 1 degree. Then relative humidity is there. Then after that it is valid up to, so it is valid up to, you can say 28/11/2016, that is the date of validation. Now this may valid this may vary. That is the frequency of the calibration. Many times this question is asked, what should be the frequency of the calibration? The ideal answer is that the frequency of the calibration is not fixed. It cannot be generalized. The frequency of the calibration should be decided depending upon the use of that particular instrument. If the use of the instrument is very limited one, you are using that instrument rarely, then there is a no question of the wear and tear of the instrument, and there is no possibility of carrying out the maintenance, and so in such case there is no need of the frequent calibration. But if an instrument is being used frequently, then in that case there will be definitely wear and tear of the mechanical parts, and error may get introduced. So in that case the calibration can be done, has to be done frequently. So this question is asked many times by the examiner at the time of the oral. So that you please keep in mind that the frequency of the calibration is definitely the function of its use. And last part here is the calibration observations. So as I told you that this is the standard reading, this is the observed reading, and this is the error. So conditions of the anvils is flatness is given, parallelism is given, and some remarks are given, and then finally it is checked by and the approved by. This is just for your information. With this we will stop today, and in the next lecture we are going to start the another concept, that is geometric form measurement. Okay, so we'll stop here.